thank you so much. And yeah, thank you everyone for joining me. Get to talk about my favorite stuff, computer architecture, and some of the cool things we're doing. Because our group doesn't have a product yet, I can't go into too much detail, but that's actually more fun because I can talk about the broader trends and exciting things we're doing, rather than trying to sell you something. So yeah, as Patrick mentioned, my name's Arun. I'm at Samsung. Standard disclaimer, the views presented in this talk are just what I think, not necessarily reflecting Samsung's views, and these do not reflect future Samsung products or roadmaps or promises or contracts or anything of that sort. So with that, I think Patrick already covered my pedigree, started for a name. My PhD topic was programming future architectures, dusty decks, memory walls, and the speed of light. I'll talk a little bit about that, but it's basically processing and memory stuff. I spent 15 years at San Diego where I worked on a whole bunch of things, and probably most notably the Structural Simulation Toolkit, which is a general purpose framework for architectural simulation. And then the last couple of years I've been at Samsung as principal engineer of HPC and AI application performance modeling, a title which I'm still trying to understand exactly what that means, but seems to be a lot of fun so far. And my major accomplishments in life are that I have won 3 ribbons at the New Mexico State Fair, including 1 Best in Show in the Pecan Pie category. So that's really my legacy, but for logistical reasons, we'll mainly talk about computers. So, as I said, from Samsung, if you're not familiar with Samsung, we make everything. We made that, and possibly some other things. Here, we make a lot of computers, probably some of the cell phones in your pockets, a lot of networking equipment. They're pushing into things like transportation, smart cars, things of that sort. We also make infrastructure. So if you're familiar with the Burj Khalifa, the tallest tower in the world, Samsung apparently built that. We also built container ships, liquid natural gas ships, oil refineries, oil platforms, dishwashers, stoves, all sorts of things. So we're kind of a little bit of everything, and particularly we're the #1 memory manufacturer in the world. The group within Samsung that I work in is called SATE, the Samsung Advanced Institute for Technology Labs, basically the research wing of Samsung, and the corporate R&D center. And our goal is to kind of create the breakthrough technologies across all of these different businesses. So SATE, our goal is not to necessarily create the individual products or refine them, but to kind of create the novel and innovative ways to use new technologies to create whole product lines. Some of the things that we've worked on are Samsung's first neural processor, some of our first OLED displays, different applications of quantum dots, batteries, biometrics, and everything down to device physics. So basically this means that we do a lot of things, and as a result, because all of these things require computational modeling and analysis, Samsung actually has a pretty long history in supercomputing, but primarily as a consumer rather than a producer of supercomputers. All the way back to the 90s, we had some fair number of Cray vector machines. In the 2000s, we did a lot of internal grid computing, and now, of course, it's the era of machine learning and things of that sort. And so, we actually have a computer, one of our internal computers, SC21, which is on the top 500 list. And because we care about so many industries, we use these computers for all sorts of things. Our fab groups need them for molecular dynamics and kind of traditional HPC applications. Designing container ships, understanding how like finite element simulation impacts things is important. And of course, the wide variety of AI and ML technologies, which we're putting into all sorts of products, from cell phones to supercomputers. And in order to support all of this, we need to understand what trends there are in computing and how to create computers create or purpose computers for ourselves. So a major goal of the System Architecture Lab, which I'm part of, is to address these internal needs and address external needs. Basically, Samsung historically is a component company. We make memory chips and we fab chips for other people. But to really make those chips better, we need to understand a computer from a systems perspective. So rather than just our customers coming to us with specifications, we want to be able to go to our customers and say, to really build a system, here's what you need, and let's work together to build it and create something new and novel. And to do that, we need a lot of internal supercomputers, but we're also trying to understand how to build better supercomputers and better computers in general in order to support this. So, with that as a preface, to talk about where computer architecture kind of is coming from, how it's been motivated, and where it's going. So, I'm an HPC person by background and preference, and HPC is kind of dominated by these star computers, leadership class machines, which are some of the largest supercomputers in the world. The chart here kind of shows the information from the top 500 list, which, if you're not familiar, is a list that's put out twice a year, ranking the top 500 biggest supercomputers in the world by using a benchmark called LinPack. And we can argue about LinPack being a good benchmark, but it's kind of what we have and how we rank things. This chart, the bottom axis is year, the y-axis is number of flops per floating point operation per second, and the three lines show the number 500, so the slowest computer on the top 500 list. The red line in the middle shows the number one computer on the top 500, and the blue line shows the sum of all the computers on the top 500 list. And what you'll see is that these lines are going up really quickly. Over the past few decades, we've averaged about a doubling in that red line every 1.3 to 1.5 years. And if you think about that, that's really impressive. That's faster than Moore's Law over that same period of time. So it means not only are we taking advantage of having more transistors and better transistors and faster transistors, we're also just building bigger machines. So we're taking advantage of more and more parallelism, and we're making architectural advances in order to get all of those things actually useful and usable, and be able to harness all those new transistors. And a number of leadership class machines over the years have exemplified this. Things like Intel Paragon, which had some of the first, really emphasis on parallelism. ASCII Red, which had, interesting ways of accelerating communication. Machines like Roadrunner and Frontier, which were heterogeneous and used different types of computational cores in order to achieve better performance. And so, basically, we've gotten better faster than Moore's Law, not just by kind of riding the current trends, but by really advancing those trends in different ways and making architectural progress. What this means is that supercomputing has been a history of discontinuities, where the prevailing paradigm of how we build a machine is changed radically, and we kind of come up with a new way of doing things, which kind of radically changes things. From some of the earliest discontinuities were the Cray vector machines, where we went from doing single instruction, doing a single computation, one instruction doing multiple computations, and amortizing some of the cost and improving the parallelism. Later, with the Beowulf revolution, we switched from very customized cores to more semi-custom microprocessors and commodity microprocessors, allowing us to take advantage of the economies of scale in the industry. Later in the 2000s, multi-core and multi-threaded processors started to dominate as fabrication allowed us to stick more cores in a smaller amount of area. Things like Blue Gene were a real exemplar of using a number of lightweight cores to kind of bring massive parallelism to a problem in order to solve it faster. And now one of the big current trends is the idea of heterogeneity. This is usually done in the context of GPUs, where we have GPUs and CPUs in the same system and kind of partition the task wherever it's best. But we're also starting to see glimmers of new and more exciting ways of creating heterogeneous systems and improving the performance by specializing. And there are kind of a history of even earlier discontinuities, which we all kind of take for granted. The move from mechanical and electromechanical computation machines to vacuum tubes was kind of what started the computers as a thing. Architectural or system-wide designs like the von Neumann architecture and stored programs kind of changed a computer from a thing you had to change the wiring of to get it to do something new into something which you can use the memory of the computer itself to customize it. And of course, the transistor, a lot of orders of magnitude changes, and allows us to, today utility machines where the smallest parts are measured in tens of atoms across, which is kind of mind-blowing when you think about it, but we deal with it every day. And then, integrated circuits as we put more and more transistors on the same portions. And in parallel with the idea of integrated circuits, the Meade-Conway VLSI revolution, where not only do we take the technical ability to put lots of transistors together, but we then needed a corresponding revolution in how we viewed the chip, how we designed it, meaning that chips could be designed by people who were not physicists and device physicists, but that it kind of broadened the applicability of who can design a chip and how we can do it, and then paved the way for things like IP reuse and just generally a lot more flexibility in the way computers are created. And memory has also seen a number of major discontinuities, from old mercury delay lines where you'd use like a waveform propagating through a big tube of mercury to store information, to drum memories where you have a big spinning thing that you lay information on, to magnetic core memories, and then the big change to single transistor DRAM, which allowed us to keep our memory storage on the same track of taking advantage of fabrication advances that we had for our processing elements. And kind of similar advances, every day with new non-volatile memories and different device physics, which we can take advantage of there. So, a lot of these general, challenges to make computers faster, we kind of address with a series of general solutions. Broadly, there are kind of two sides of these: the hardware and the software side. The hardware side, is not just the architecture, but also the physical design, the manufacturing processes, things like packaging. All of these things kind of come together to enable new capabilities, which we can then exploit. And then on the software side, there are other things which are sometimes more difficult to measure, but equally important. How programmable is a computer? How easy is it to use? And a lot of these are often kind of social aspects of not just, is this the best way of solving a problem, but is it sustainable? Can people actually use this in a way that suits them well? That's why things like Linux have been very useful, not because it was inherently better than any of the other dozens or so Unices that used to kind of play over the market, but because it allowed us to use computers in a way that was socially easier and more sustainable. So on the hardware side, these very general solutions have kind of three buckets of kind of slightly less general ways of addressing things. In hardware, our probably number one thing is we smush things together. And we do this to reduce overheads. So, with VLSI, we took, thousands of discrete transistors and stuck them together into a single piece of silicon. With things like vectors, architecturally, we took one instruction and allowed it to operate across, many pieces of data rather than just one, reducing some of the overheads. With multi-core chips, we take these large chips and kind of smush them together onto a larger piece of silicon in order to get, better performance. Because they're closer together, there's less overhead in moving from one to the next. So switching things together is the big part of how computers have gotten better. We also have some other techniques. We specialize. Instead of having a general purpose transistor, we do things like GPUs or other accelerators. And basically, we limit the scope of applications that a particular circuit is useful for, but we find that narrower scope and do it better than if we have a more general solution. So we specialize things. And then sometimes we just do things better. We replace our vacuum tubes with transistors and get orders of magnitude improvement. We replace our magnetic cores with DRAM and our orders of magnitude smaller, things of that sort. So on the hardware side, we have three things, and on the software side, there are three other techniques. So in software, we pull things apart and we add overhead. We call these abstraction layers and libraries. And they allow us to interface better with the computer by separating concerns into different buckets, but at sometimes the expense of overhead. We also generalize. We create programming languages which can run on a number of machines. We allow compilers to kind of do the heavy lifting and optimization. And in software, we do things worse, like Microsoft Outlook, and increasing complexities. From this list, you may be able to discern whether I'm more of a hardware person or a software person, but I'll leave that to you. So how does this impact the next discontinuity? From these kind of general solutions, we can kind of predict what the next discontinuity is going to be. And I believe the next discontinuity will be a set of techniques which we call closely coupled computing. The idea of bringing things, compute, memory, and communication closer together. And this kind of follows our normal ways of addressing things. We smush things together. Using packaging technology, we bring things physically closer together. We make the interfaces between them lighter so they're easier to get to, lower latency, and reduce power. We specialize. Instead of just having kind of uniform compute cores, we'll have different types of compute cores and accelerators, as well as other accelerators for things like making communication specifically faster or specific portions of communication faster, as well as some other accelerators for compute assist that I'll talk about. And then we do things better. Our packaging improves, which allows us this tighter integration, but also gives us some interesting possibilities for making the programmer's job easier, rather than having to figure out how to hide latencies. If we can bring things closer together, we can allow the programmer to focus on the main task of programming rather than spending as much time optimizing. So, with those very high-level general problems, general solutions, and directions for the next continuity, next I'll talk about some of the specific challenges which we face. And I'm going to reuse a graphic which I used for my PhD many years ago, but which is still relevant, that we face challenges in dusty decks, basically old software and how we migrate that software. We don't actually have punch cards anymore, but the spirit of having a giant stack of punch cards, which you've got to run on your machine, still is very strong with us in a lot of ways. Memory walls are still a big challenge. Getting data from one part of the computer to another is still kind of one of our fundamental design hurdles. And then the speed of light. Basically, we have physical constraints which we have to adhere to and have to find some way around. So dusty decks, software is of course why we have computers. And for most large organizations, a lot of times the software investment is much, much larger than the hardware investment. Coming from Sandia and the DOE, we would, on a fairly regular cadence, build these $100 million machines, which seems like, quite a big investment. But compared to the billions of dollars which we invested in software over, decades or even generations, the hardware cost is, kind of the almost secondary to making sure that the software investment is maintained. And so there's a constant tension between getting things to run fast, but also, maintaining this backward compatibility. One of my favorite stories about how long-lived code can be, when I worked at my first internship at Sandia, worked on a code called CTH, which is a shock physics code. And there's a great comment somewhere in there, which was, had to change this to comply with the new Fortran 2 syntax. Fortran 2 was released in 1958. CTH, I think, ostensibly was created in 1965, but clearly it contains some bits of code which had existed far beyond. So this is a code where, that's literally generations old, and which is still, a major code of importance at the labs. So codes can take a long time, and that's good. We want, the physicists and engineers to focus on the physics and the engineering, not to worry about porting their code every new generation of machines. A lot of these codes are, still MPI is the bread and butter for large HPC machines. Sometimes it's MPI plus X, so there'll be MPI plus another way of expressing parallelism, like OpenMP or CUDA. But a lot of these codes also don't port well to GPUs. Some of them do port very well, some of them have been re-architected to, but a lot of them are just very irregular and just don't want to fit themselves into the GPU box. So we have to figure out a way to support that. And many of these codes, as I mentioned, are still in Fortran or partially in Fortran, which means that there's a whole set of optimizations which we might not be able to apply, or which there might be other optimizations we can apply. So dusty decks is going to be a big problem for the future of hardware, but there are some potential paths to the future. These codes, they can change, but we need to find a way to preserve as much of the existing investment as we can. Sometimes this is more of a social problem than a technical problem, just making sure we have migration paths in place. But there are also frameworks like Cocos and Raja and others which are becoming increasingly popular as sort of a high performance portability hardware abstraction layer, so that we can write codes in such a way that they can make good advantage of the hardware, but not have to be drastically changed every time new hardware appears. So dealing with these dusty decks, there's no easy solution, but there's sort of an evolutionary and iterative path which will allow new programming models to emerge and to take advantage of new hardware capabilities. The next kind of high-level problem is memory walls. It's kind of a truism, particularly in HPC, that data movement dominates. HPC programs are really memory applications, or memory transfer applications. Although, as I mentioned, we use LinPack, this very floating point intensive code to kind of rank our supercomputers. Realistically, real codes don't really do that. Most of the instructions inside of an HPC production application are not going to be floating point. This chart here shows the dynamic instruction mix, the instructions that are actually executed, kind of averaged across a range of applications at Sandia. And you'll see most of them are memory instructions. That's the biggest block. You also have some branch calculations and things like that. And then a lot of integer computations. And then you've got a little bit of floating point. It's not uncommon for HPC application to have well less than 10% of its instruction mix to be actual floating point, because most of the time you're doing memory and integer. And of those integer operations, if you look at what those integer operations are actually doing, most of them are computing either floating point or integer addresses to load. You do some branch stuff and some pure integer. But generally, HPC codes do a little bit of floating point, but mainly they're memory codes and integer codes, and the integer operations are computing memory addresses. So memory is really what dominates HPC. And as the physics that we want to simulate, the engineering becomes more complicated, most frequently we'll see that the codes themselves become more complicated as we need more adaptive data structures and more complicated algorithms to simulate what we need to. This is true of HPC. AI is a little different. It tends to be a little more regular, a little more floating point intensive, but even AI and ML tends to be evolving. There's often lots of data pre-processing which has to occur before we can actually get to the citing part of the AI application, and a lot of times that will be very memory intensive. And then things like graph neural networks or other types of ML algorithms are starting to become more irregular and less floating point intensive. So figuring out how to address this memory wall is going to be another challenge for future architectures. And then there's the speed of light. Fundamental physical limits, we just can't change these. But we can kind of cheat and sneak around the side. Particularly by new packaging techniques for closer integration, like 2.5D, 3D, or chiplets, can allow us to bring the different parts of the computer closer together. And we have new emerging technologies like optical communication, which still obeys the physical limits and the speed of light, but allows us to kind of move photons instead of electrons and gain a lot of benefits from doing that. So dusty decks, memory walls, and the speed of light are the challenges which we face. We have kind of this bevy of techniques to address them by smushing things together, specializing, and just doing things more efficiently. And so that leads us to kind of the specific solutions which we are going to be seeing for future architectures. So the specific solutions which I think are going to dominate kind of fall into three major categories. One of them is advanced packaging, which is kind of the key ingredient to close coupling. And this takes a couple of different techniques. One is closer coupling between the memory system and the compute. So we have things like 2.5D and 3D integration, where instead of having discrete chunks of silicon with circuits on them, we bring these together. In 3D, we stack them on top of each other, making the distance between one level of circuits and the next in the tens of microns or even less. And then in 2.5D, we keep things in a 2D plane, but we take a number of chips or smaller chips or chiplets and kind of attach them on a silicon interposer. So we're still sending circuits over, like copper wires on silicon. So we still have very high performance, and we don't have thermal mismatches and expansion problems. But we're able to get things much closer together than if we just have them on discrete packages. And then there's also chiplets, the idea of breaking a large compute block into several smaller ones. I'll talk a little bit more on that. And then, just as important as physically close is the idea of bringing things architecturally closer. So, the person programming the computer or the person using it, they don't actually really care whether you've got a bunch of packages or a single package. And that's not something you can see when you're, writing your Python code. What we do kind of get glimpses of, though, is the architectural way of how do the parts of this computer interact. And this is another area where we need to bring things closer together architecturally in order to eliminate some of the overheads. A big thrust of this is the idea of combining general purpose CPU cores with high efficiency accelerators. And doing so not in the way that we kind of currently do, where often they're physically relatively close, but architecturally they're on the other side of, say, a PCI bridge or something like that, and dealing with them is kind of a hassle, but by making them architecturally and programmatically close so that the CPUs and the accelerators really live as kind of first-class citizens in the same memory space and on the same communication network. And then there's a number of other accelerations you can do to make the network go faster. There's work in topologies, breaking networks into multiple layers so that we can have good point-to-point and simultaneously good all-to-all communications. But this also requires support in the runtime. There are different ways to accelerate collectives, both algorithmically and in the hardware. All of these things kind of come together, and they take advantage of the architectural and packaging close coupling. That if we can bring the network interfaces, that NIC, closer to the CPU cores, and treat it as a first-class citizen, not as a device across a series of bridges, then that allows us to open up new programming models and kind of further reduce latencies between network endpoints. So all of these specific solutions are very good, but they also raise a lot of questions and require a lot of design decisions. Lurking beneath all of this is the great dread which haunts hardware designers, which is software. The question always is, we can build hardware really fast. We can cram as many floating point units as you want into a small area, but will it actually make the applications faster? As showed earlier, HPC applications, really don't do a lot of floating point. They're mainly spending their time mucking around with memory. So even if we make, the math part really, really fast, does that actually address the problem? And so we need to figure out how can we program this. Does having all this close coupling help us make things easier, or does it just introduce, trade one set of problems for another? So these are the questions we need to look at further. So I mentioned advanced packaging. 3D packaging is a direction that the industry is moving towards. Already a lot of memory, HBM memory is 3D packaged. This allows kind of the closest connection between right now memory to memory and starting to get memory to logic. Some of these are about 0.1 to 0.01 picojoules per bit, which means that transferring large chunks of memory takes quite a lot less power than it used to. But the downside of thermal packaging the downside of 3D packaging is thermal issues. When you have one CPU or one compute chip, which is burning 100 watts, that's hard enough to cool just in its own package. When you've now crammed several layers of additional silicon on top of that, you've essentially created a number of insulators on top of your thing, which is already hard to cool. And when you then fill those insulating chips with DRAM, which has difficulty storing electrons in its capacitors, as they get hotter, you've added even more complexity and more difficulty to your thermal problems. There are a number of solutions from this, or attempted solutions, things like just making the system liquid cooled, or even pumping coolant directly into the chip through micro channels, or even more exotic like phase change materials. And these show a lot of promise, but they also add a lot of complexity. And ultimately, designing a cost-effective system may make them more difficult to implement. So 3D is very promising, and it's certainly useful in a lot of areas, but it has its own set of issues. 2.5D is kind of a nice trade-off between these. The idea of putting things on silicon interposers, so they're still very close, but they still have enough surface area so the thermal issues are easier. here the power consumption is between like 1 and 0.1 picojoules per bit. So not as bad or not as good as 3D, but still much better than discrete packages, which would be in the often multiple picojoules per bit. And then kind of related to this is you have chiplets. You're using a series of small chips kind of connected together rather than one large one, which I'll speak on a bit more. But underneath all this is, again, that lurking dread of software. Does adding all this integration just make things easier, or does it just mean that now we've got a lot more non-uniform memory access domains to deal with? From the software perspective, it's enough of a pain having to break your program into MPI chunks and communicate across the network. And then if your individual CPU cores have different memory access latencies, that means you have to account for that when you're doing things. And now we're moving to a world where you might have to worry about, well, how is this accelerator next to memory? Is it stacked on top? Is it stacked next to it? Is it stacked across a DRAM bus? Is it across a PCI? All of these additional things just become potentially more headaches for the programmer. In the best case, that means that they have more opportunities to optimize. In the worst case, they just say, I'm not going to do that. Stick everything in the slowest type of memory because I know it'll be uniform, and then we're back where we started. And another concern, which often comes up when the hardware people show these sorts of graphs to the software people, is this something I'm going to have to care about? Is my software going to have to worry about thermal issues and selectively turn things off or throttle back when a temperature reading gets too high? Because I don't want to do that. I'm a physicist and I want to do physics. And again, best case, they can find some exciting things to optimize and get some papers. Worst case, they just say, I'm not going to do that, and the chip burns. So, and underlying a lot of this is the idea of cost, and this is where chiplets come in as a major technology moving forward. The basic idea of chiplets is, instead of having one large monolithic piece of silicon, break that into multiple smaller pieces of silicon, which are in aggregate cheaper, and allow you to get better performance by stacking more of them together with 2.5D or 3D integration. The way that this becomes cheaper is basically through how chips are fabricated. With smaller chips, you can fit more of them on a wafer. The cost for fabricating one wafer is more or less constant. So you can get more chips out of it. That means each chip is less expensive. And with smaller chips, we still have to worry about defects in the wafer. And with one big chip, if you get one defect in the wrong place, that means you have to throw out the whole 500 square millimeters of chip. So if we have lots of small chips, then there's less to throw away when we get those inevitable defects. You can kind of see this, just a very quick study of two different chip repairability architectures. You can get around some defects of repairability. This shows the chip area and then the kind of normalized cost per square millimeter. And you can see it's not a linear growth. As the chips get bigger, you have this kind of exponential explosion of the cost because you have to deal with more defects and have to potentially throw away more of the chip when something goes wrong. So that's the basic idea behind chiplets, is to make things cheaper. But there's some other really interesting possibilities. One is that we can kind of mix and match process nodes. Right now, if you have a 500 square millimeter GPU, it's all made in the same process. But do we actually need the latest, greatest process for everything? Something which has happened over the last 10 years is that the latest processes, they're smaller transistors and they have better density, but the actual cost per transistor has not been getting better. Which means that to fabricate something in 3 nanometer is more power efficient than say 5 nanometer, but the 5 nanometer might actually be more cost efficient. And there are lots of parts of the chip where you don't necessarily need the smallest transistors you can get. If you're doing something like designing a PHY to send a signal from one place to another, you're just going to be using big honking transistors to begin with, so there's no reason to use the smallest transistor process. You can potentially use a larger one, and then save cost by using a less expensive fabrication process. And there are other interesting things you can do with this kind of mix and match chiplet idea. One of them is heterogeneous integration. So you can integrate things like silicon photonics, which tends to use 3-5 materials rather than traditional silicon, along with your CMOS chips, so that you can do very close integration of these two things. if you needed to do this in a monolithic form factor, you'd have to have a very, very complicated fabrication process, which can put both silicon and 3-5 materials into the same thing. And I'm not a fab guy, but the fab guys look at me angrily when those ideas are suggested. So being able to run them on separate fab lines would give us a lot of benefit. And there might be interesting things from a kind of business standpoint that we can have, custom silicon integrated with, kind of stock off-the-shelf silicon. So if you're, a particular company, be it a national lab or a financial services firm or an AI startup, has discovered some exciting new circuit or some exciting new accelerator that can make things better, but they still need a regular CPU and some other accelerators to drive the rest of the computation, you can, fabricate your piece and then in a very close manner integrate it with other components, in a series of chiplets, which allows you a lot more flexibility. But again, we have this lurking dread of software. Does mix and match mean more flexibility, or does it just mean more complexity? And is this something which we can program? How much of this can be hide? Does a programmer have to worry about breaking up their application into 10 different types of accelerators? And at what point do they just say it's not worth it? Just give me a CPU or GPU, and I'll be fine with that. So this chiplets open up a lot of possibility, but it's a balancing act within there. Another interesting technology is optical communications, things like silicon photonics. One way of explaining silicon photonics is, it's sending photons instead of electrons. On your computer chip, you don't have a little generator to create your electrons for you and charge them. You bring those from outside. Similarly, it's more efficient to have an external laser which pumps your photons into your chip, and then you have some, simpler structures in there to modulate them and send them, send them to where they need to be, rather than, having to do that all on chip. Silicon photonics is really great because it allows us to send signals across very long distances. For like copper signaling, generally it's hard to do more than a couple of meters or even less now at high speeds. But with silicon photonics and optical communication, we can send things for hundreds of meters, even kilometers, without using much power. But again, there's this lurking dread of software. What does this mean for programming a system? One problem with some silicon photonic implementations is that the switching is much slower. So with electronics, we can basically shunt electrons whichever which way we want very, very quickly. And we don't have to worry about that. This is what allows us to build the internet out of packet-based routing, that we just break our message into small bits, shove them through a network, which throws them wherever they need to be until they get to the endpoint. With photonics, this might not always be the case. The switching latencies might be in the microseconds or even milliseconds for some technologies, and so we might have to go back to something like the old phone system where it's circuit switched, not packet switched, where you essentially have to reserve a pathway through your network topology before you can send data. This could be more complexity for the software. It could constrain the types of network topologies we build, or it could maybe allow some interesting optimizations and kind of make us refactor our programs to be more efficient in different ways. So again, we have a series of trade-offs. And then another area is the accelerators. What we're seeing now has been called by some a Cambrian explosion. I think it was 500 million years ago. Life had to be very simple, single cell, not very interesting. But then suddenly something happened and life started to get more complicated. We see this huge explosion in the number of species that populate the world. We're seeing something very similar with architectures and accelerator architectures today. GPUs, kind of broke down the barriers and got a lot of programs to rewrite themselves to work on these more efficient architectures. And now we're seeing similar things with AI accelerators or CGRAs, coarse-grained reconfigurable arrays, kind of like FPGAs, but with ALUs instead of lookup tables. And there's a wide variety of these things, which are all competing, and some which are only useful for very niche applications, but which have a lot of possibility for how we can program things. In addition to the compute accelerators, which people tend to think of, there are also potentials for communication acceleration. So things like doing protocol offload. If you programmed an HPC, you probably programmed an MPI at some point and seen the complexity that MPI can have and all the sort of tag matching and messaging semantics that it requires. These things are very kind of painful to do in software, but can be done with relatively simple hardware structures and potentially accelerate things a lot. Similarly, by moving a lot of some of the computation into the network to do things like collectives, like all reduces and things like that, you can again reduce a lot of the power that it takes by getting the CPU kind of out of the main line of computation and overall improve performance. And there's, I think, a whole other type of accelerators which we don't talk a lot about because they're small, but which are equally important. What I call kind of compute assist processors. These are things that do the computation, but they make it easier for the computation to occur. Already in GPUs, you see thread management and dispatch done at the hardware level. Rather than having to have the operating system take an interrupt and tell each thread where to go, you can just have a simple hardware structure that breaks a problem, breaks a problem into a number of threads, and then distributes those into different hardware queues, making it much faster and relieving the programmer and the operating system of those issues. I think you can expand on these kind of thread dispatch structures. Bring thread dispatch across networks so that whole nodes can be can kind of move the compute through a network in order to move the compute to where the data is, rather than having it kind of statically assigned, and that opens up a lot of possibilities for programming. There are other things, just like simple queue structures. Pretty much every program will use queues in different ways. And if you have hardware deal with some of the queue semantics and handling, that's another useful potential mechanism to accelerate things and reduce the load on the conventional processor. And then there are inter-process communication mechanisms. Right now, inter-process communication often involves kind of complicated dance of locking and unlocking and difficult memory semantics to move things across. But in the embedded world, that isn't always the case. There are simple mailboxes, simple hardware scratch pads, which allow very fast communication between between adjacent processors, and we can do something similar for more general purpose processors. And so we have a lot of capabilities there. But again, we have the lurking dread of software. A software engineer would say, it's bad enough they've forced me to break my problem into MPI chunks in order to get parallelism. Now we want to break the chunks for GPUs, and that's annoying, but we'll live with it. Now you've got 5 different types of accelerators, 3 different types of compute assist whatevers, and communication offload, so I don't even know what's going on when I send a message. All these other problems, have we really improved performance, or have we just added headaches to someone else? As long as they're software people, I'm okay with that, but the wider industry might not be. So as I said, there are lots of these trade-offs, lots of complexity, and it requires innovation across a number of hardware and software domains. To really deal with this, we can't just design things in isolation. We have to do system co-design. Essentially, the hardware and the software need to work together. As we get things more and more closely coupled, this requires a more holistic kind of system view of how all of these different parts work together. And to do this, there's no one methodology. Already when we're designing things, there's a wide range of processes for this. Everything from quick estimates, spreadsheet models, different types of architectural simulations. Then as we get closer to the product, RTL, physical design, and so forth. Similarly with software, there are lots of high-level models, algorithmic explorations, big O analysis, emulators, software prototyping, all these things as you get closer to the actual production code. But doing all of these things when actually creating a product is very complicated. And as we get more and more closely coupled, we need a way of reasonably communicating these things across each other. And this is where things like the SST simulator, which I work on, kind of enter. Basically, SST allows us to bring together lots of different components in a system in the same simulation environment at different levels of scale in order to simulate them and explore hardware and software at the same time. This is an old marketing slide from Sandia, but basically the goal of SST is to use the supercomputers of today to design supercomputers of tomorrow. It's a parallel simulator, which means it's much faster. We can look at bigger systems. It has this idea of multi-scale operations, so rather than just saying we do everything at cycle level, we have some components which are cycle level, some which are much more abstract. and kind of a range in between. And also it's kind of open, both in the sense of a non-viral license, and also it's designed to be modular, so it's easy to plug different components into each other. SSD comes with a variety of components kind of out of the box. Everything from cache models and processor models to very low-level models like ability to interface with RTL, and even much more high-level models. So you can look at a million endpoint network. And SSDs gives you all these technical capabilities, but it also is a really useful tool for research on a social level. It creates a common platform for design. At Samsung, we have a group which is spread all across the U.S. and then another group in Korea we interact with. And because of the spherical nature of the planet, we only have a few hours where we kind of overlap being awake. So having a common platform where these things can kind of come together and allow us to have a single source repository and look at the problems together is very useful. It also allows us, because it's modular, to interact with other simulators like System C models or Joan 5, and really allows us a new level of collaboration, both within our research group, but also potentially with suppliers, future customers, or other researchers at universities or elsewhere. And most importantly, SSD, because it looks at everything from the software to the hardware at the low level all the way to the high level, gives us kind of a unique ability to learn how to analyze the system. We can take big problems, break them into smaller problems, look at different algorithmic approaches, and overall build a system modeling capability which we would not have otherwise unless we essentially reinvented all this from scratch. So some of the big challenges we're looking at now are, how do you simulate a system with 1 million cores, and how do you do that in enough detailed build confidence? And the approach which we're using with SSD is kind of to both combine these high-level abstract models, which we call motifs, with lower-level models for cycle-level models, and then kind of feedback between them. A lot more detail in there, but essentially we can use this to represent programs at any level of detail we want, from essentially a spreadsheet model or an algorithmic description, all the way down to actually executing it on simulated RTL. We can leverage a number of existing components within SSD to look at everything from the core to the cache to the network on chip to the network topology. And it allows us to do a number of really interesting trade-offs in terms of how much speed do we want from the simulation, how much detail do we want, how easy is it to use and to program and explore with, and how scalable it is. By having this kind of grab bag of simulation capabilities, we can mix and match within there in order to do what we need to. This allows us to explore a wide range of design choices, things in the core, looking at different cache configurations or internal structures and queue sizes. And we can also look at things like optimizing different kernels, looking at what compiler optimizations might we need to take advantage of a particular hardware organization, or what algorithmic changes we make. So, in summary, HPC and AI systems have a lot of general challenges which we've been facing for years. Physical challenges, manufacturing challenges, and then kind of the programmability and software challenges. Historically, the industry has always found a way over these discontinuities, these substantial leaps forward in how things are done. And the next leap forward is going to be by increasingly tightly coupling, specializing, and taking advantage of new technologies to create systems which are much more closely coupled than they ever have been before. But to actually take advantage of this and to make sure we get a system that not only has good specs, but we can actually program, we need to embrace this idea of system co-design. So we can look at everything from the software to the hardware. And tools like the Structural Simulation Toolkit provide a good framework, both at a social level and a technical level, to perform this system level co-design. Thank you.
I'm going to make a quick announcement before we take two quick questions from everyone. So first, I just want to thank you for being our inaugural speaker, and I have to read this, in our Clean Moeller and MathWorks Chair in Mathematical and Engineering Software Distinguished Lecture Series. So we really appreciate I know quite a bit. For the students in the course, your quiz where you answer questions about this talk, which should be a lot of fun, is now posted on Canvas. Hopefully most of you have seen that. And I think we have time for questions. So I know that we packed a lot in there. I learned a lot. Any questions from the audience?
Do you think we're at a point in this kind of software thread where we're forcing the software developers to know too much about the underlying technology?
Yeah, that's definitely a concern. I think at DOE, they often talk about the idea of hero programmers who, are people who know the algorithm, the application, the physics, all the way down to, what the cache is doing every cycle. And they, can get incredible performance out of machines, but there are very, very few of them. For a physicist, every second you spend thinking about cache performance is a second you're not thinking about physics. So there is definitely a problem. So yeah, I think that is going to be a problem. Some of the ways which we're hoping to address that are through some of these libraries like Cocos or Roger, which allow portability. But I think there's always going to be a trade-off and attention there that to really get the next level of performance, you probably always need a little more knowledge of the hardware. So it's just a question of, can we also construct hardware which is powerful but simple enough that it can be reasoned about. Like in the embedded world, for a long time, many embedded applications shunned the use of caches, even though they knew caches improve performance, but just because it was too difficult to reason about. And if you need to make sure that your computation completes in a certain amount of time, or the plane falls out of the air, you're willing to sacrifice performance for simplicity. And so, as hardware designers, we need to kind of figure out what is that right balance point as well to make sure the software can come along and reason about the hardware in useful ways. And sometimes that will mean giving up some performance if we can reach a broader audience.
You mentioned in the beginning of the talk that you do work in AI as well. Are there ways to leverage AI in hardware design, or is it purely sticking things together physically?
Yeah, I think there definitely are. Based on research proposals, everything has got a way to use AI. So yeah, I think a lot of those things are still emerging, but certainly some of the areas where we have been using AI are being able to kind of help with experiment design and sort of do more guided simulations. Like with a lot of hardware design choices, you've got 10 different components, each of which has 20 different settings. And if you want to brute force explore all of those, you'll have to do millions upon millions of simulations. So there are a number of machine learning techniques we can use to kind of prune that design space without losing too much accuracy. That's something which is already in use. And then I think, yeah, there are a number of areas where we can use AI to kind of more artificially intelligently explore different ways of connecting components and understanding how the system as a whole is working.
Excellent. So, Arun, or Arun, I think your name.
Please
agreed. If anyone wants to talk about research or possibilities of in working at Samsung, there's an expert right here, so he'll be around for a few minutes. So feel free to come up and chat. And thank you.